This will be mini lecture 25. Today, we're going to be looking at an example of a second order circuit. And if you remember anything from the last lecture, we looked at the three cases of solutions that come from the differential equations, the type of differential equation we can have. And today, we're going to look at the case of an underdamped example. We're going to use a circuit to kind of really look at these cases, try to learn from them and see how we proceed. So let's bring an example up so that we can look at that. So this is the example that we'll be looking at today, or we'll be using to kind of really discuss the underdamped case and how that plays out from the differential equation here. So we're looking at a circuit here. So a little bit of a review here. We're looking at second order circuit. And when we think about second order circuit, we are looking at, let me see here. We are looking at circuit that have two storage elements. In this case here, I can see a 0.8 farad capacitor and a 1 Henry inductor. So you should expect that a second order circuit is going to produce a second order differential equations. We're looking at second order differential equation with constant coefficients and potentially constant right-hand side. When we look at these circuits, much like when we look at in first order circuit, we're looking at circuits that have constant sources. In this particular example, we have a 1 amp source. What's causing a change in the circuit is the switch. A switch that's either opening up or closing. This particular example here, the switch is closed before t equals 0 second. So up to t equals 0 second, the 1 amp is connected to the circuit. And at t equals 0 second, the switch opens up, disconnecting the 1 amp. So what we've been discussing essentially in these types of circuit, for t less than 0 second, what do we have here? We have a circuit that looks like this. So the switch is actually connected, okay? But this has been a circuit that's been in a constant source situation for a very, very long time. So when that happened, we essentially can conclude that the capacitor behaves like an open circuit. In essence, because of the capacitor current voltage relationship, if there is no change in the circuit for a very long time, the current must be 0. So we represent that as an open circuit. Similarly, for the inductor, when the inductor is in a circuit that has a constant source for a very, very long time, as in the situation here, we're looking at it as the inductor behave like a short circuit. So the circuit we actually really solving essentially for t less than 0 will be this circuit. Can be represented by this, with the capacitor behaving like an open and the inductor here behaving like a short circuit. So typically in the second order circuit, much like in the first order circuit, the first time period is a time period where you should not have a capacitor or an inductor in the circuit, because these circuits are excited by DC sources until the switch causes a change in the circuit, as if that happened at t equals 0. So it's fairly simple. One more point I want to make here. Even though you're being asked for the inductor current in this case, you also need the capacitor voltage. So we've talked about in the past of initial conditions. Initial conditions come from two things. That comes from the capacitor voltage. Now, you have an option of putting the polarity however you want on the capacitor, but you need the capacitor voltage. You also need the inductor current, although that's what was asked, so it suffices to say you would need to calculate it. The reason we need the inductor current and the capacitor voltage, because these are related to the energy in those elements. The energy in those elements are really the initial condition, are really where the initial condition come from. So no matter what you're being asked in these circuits, you always need to calculate the capacitor voltage and the inductor current. Of course, the inductor current if you're dealing with second order circuit, if you're dealing with first order, one or the other. So in this particular case here, I can clearly see that the inductor here shorts the 4 ohms because it's in parallel with the 4 ohms. So that forces the current on the 4 ohm to be 0. So the 1 amp current is essentially looping into the wire of the inductor. Okay. And once you realize that, you realize also that the inductor is shorting. There is no current under 1 amp, under 1 ohm, because the capacitor is unopened here. So that means that the capacitor voltage is essentially the voltage across the inductor. It's 0 volts. So the inductor current is 1 amp and the capacitor voltage is 0 volt. These are going to be our initial conditions for the circuit for t greater than 0, where we will have a differential equations. So let's look at the circuit now for t greater than 0. For t greater than 0, again, the switch that was here opens up, in essence, disconnecting the 1 amp from the circuit. So you may or may not realize that once that 1 amp is disconnected, this circuit actually has no source. You actually expect to have an homogeneous differential equation. What we call this is a source-free circuit. So we're going to get the natural response for that circuit. In other words, when the right-hand side is 0. I'm going to go to the document camera and solve this using nodal analysis so that you see the steps, so that I don't do the PowerPoint skipping too much, so that you see the step by step. So give me a second here. Okay, so this is the circuit we have. Again, we're going to do it on the document camera on paper so that you see all the steps hand by hand, as if the way I expect you to do it. I'm going to do this using nodal analysis, so you're going to see the step. And my first objective here is to come up with the differential equations. Once I have that differential equations, I probably will go back to the PowerPoint and essentially complete the solution. But I would like you to see the nodal step-by-step procedure on how we get from this circuit, which is the circuit for t greater than 0, the 1 amp source has been disconnected, and we have a circuit that has no source, but it has an initial condition. The initial condition is the capacitor voltage was 0 and the inductor current was 1 amp. So I'm going to proceed now and essentially begin my nodal procedure here. So I'm going to identify the node, and I'm going to use red for my node. And there is so I have 3 nodes in this circuit here. Okay. I'm actually going to pick this node as the reference node. Okay, I'm going to pick this node as a reference node, and I'm going to name this node V1 and name this node V2. Okay, of course, this node essentially V2 is the capacitor voltage that we described before. And then I'm going to put current on my passive elements here. So here I'm going to put I1, and I'm going to put I2, and here I'm going to put I3. I already have IL on my inductor, so I don't need to add another current on my inductor as well. So in this particular case, again, when we do nodal here, we look at a particular series of steps. So what I just did here, I've prepared the circuit for solution. This is how I prepare the circuit for solution. Okay, so now what am I going to do here? I'm going to look at the various steps of my nodal solutions. Things that I typically do here, it's source equations. For voltage sources. And of course, we have none here. Okay, we have none. So we don't have to write a source equation for voltage sources. So we essentially have 2 nodes here beside the reference node. These are going to be my unknown here. So I'm going to first do a KCL at node V2. What does it give me? I1 plus I2 equals 0. So that's my equation 1, KCL. And then I do KCL at node V1. What I get in KCL at node V1, I get I1 plus IL plus I3 equals 0. That's my equation 2. So these are my 2 KCL equations for my 2 nodes. I don't have any source equations. I don't have any super node. I didn't have any voltage source in that particular circuit for t greater than 0. Then I do Ohm's law. And when we say Ohm's law, we're talking about resistors only. So I have I1 is equal to V2 minus V1 divided by 1. And then I have I3 is minus V1 divided by 4. And the minus sign is essentially because of the passive sign convention. It is where it's 0 where the reference node is, minus V1 divided by 4 equal I3. Okay. So the next step, I'm going to bring these Ohm's law. So I'm going to do KCL plus Ohm's law. That's essentially, I'm bringing the Ohm's law into the two KCL equations. You've seen me do that process, and I want to really get you comfortable doing that. So KCL and Ohm's law equation 1 becomes, right there, I1 is V2 minus V1 plus I2 equals 0. So that's equation 1 once I put the Ohm's law. Equation 2 becomes I1 V2 minus V1 plus IL plus I3 minus V1 over 4 equals 0. So in this particular case, let's get rid of the same denominator. Let's get rid of the 4 so that we put under the same denominator. I'm going to multiply the equation by 4. So what do we have here? We have 4V2 minus 4V1 plus 4IL minus V1 equal to 0. And then collecting terms, I have 4V2 minus 5V1 plus 4IL equals 0. So this is my new equation 2, and this is my equation 1 right there. Okay. So at this point here, what have I done here? I've essentially done KCL, I've done Ohm's law, I've used the Ohm's law into the two equations right there. Okay. So that's where we are here. All right. So then now, I am going to write the inductor and the capacitor and inductor relationship. Okay. So what do I mean by that? For the capacitor, I got I2 is 0.8 dV2 dt. That's for the capacitor. And for the inductor, I have, again, V1 is equal to minus dIL dt. And the minus sign is because, again, the current is going from the reference node to V1 as opposed to V1 to the reference node for the passive sign convention. So these are the two relationships here. So I get this. I have this equation here, these two equations and these two equations here that I need to essentially, now I'm going to use substitution to bring them in. I'm going to bring these equations into these two KCL equations. So let's begin our substitution here. Substitution solution. First, let's assume I use V1 here. So I'm going to use this equation. Once I use V1, I'm done with that equation. So I'm going to use V1 in the other three equations here. Okay, so 1 becomes, this one here, I have V1 here. I have V2 minus V1, so plus dIL dt plus I2 equals 0. That's my new equation 1. Okay, my new equation 2, let's see if I have V1. Yes, I do. So new equation 2 then becomes 4V2 minus 5V1, so plus 5 dIL dt, okay, plus 4IL equals 0. So I've used the inductor relationship here essentially in the two KCL equations. Now I'm going to use the capacitor relationship. And when I say use the capacitor relationship, wherever I have I2, I'm going to put 0.8 dV2 dt. So you can see that wherever I have I2, I have one place where I have I2 is right here. So equation 1, the only place I have I2, I have no I2 in equation 2, is going to be what? V2 plus dIL dt plus 0.8 dV2 dt equals 0. Okay, so now you can see, what do I have here? I have two equations, two unknowns. Two equations, two unknowns. And the unknowns are IL and V2. Okay, so I'm going to essentially use substitutions to essentially solve for either IL or V2. V2 is the voltage across the capacitor, and IL obviously is the current to the inductor. So how about if I, from equation 2, from equation 2, I can solve for V2. So if I solve for V2 from equation 2, what do I get? I get V2 is equal to minus IL minus 5/4 DIL dt. Okay. That's solving for V2. And of course, I'm going to stick that into equation 1. And you can see the differential equation coming in when I do that. So if I do that, so using V2 into equation 1, what do I get? I get minus IL minus 5/4 DIL dt, okay, plus DIL dt, okay, plus 0.8 times the derivative of this thing, okay, so minus 0.8 times the derivative of IL with respect to t, okay, minus 0.8 times 5/4 times the second derivative of IL with respect to t squared. And that's equal to 0. Okay, because 0.8, I have to take the derivative of this and multiply by 0.8, I get to this. And you can see now everything is in terms of IL. All I have to do essentially is collect term, put under the same denominator, and normalize, if you will. Okay, so I can actually just multiply the whole thing by 4. So what do I have here? I have minus 4IL minus 5 DIL dt plus 4 DIL dt plus, so minus 3.2 DIL dt minus 4 second derivative of IL with respect to t squared equals 0. Okay. So assuming that I did not make any mistake, that's what we get. All right. So I can collect terms. Obviously, I have only IL here, and I have to, these three things here, I have to collect terms. So what do we have here? I have minus 4 second derivative of IL squared with respect to t squared. Okay, so I'm going to have what here? I am going to have, this is minus 1, so this is minus 4.2 DIL dt minus 4IL equal to 0. Okay. I'm one step away from the final differential equation. Again, you forgive me if I make some algebraic error because I'm doing it on the fly, but that should explain to you the steps that you need to take. Now I normalize such that the highest derivative has 1 magnitude. So what do we have here? We divide by minus 4, so we have second derivative of IL with respect to t squared plus 4.2 over 4 DIL dt plus IL equal to 0. And then we have our differential equation. Okay. So that's the step about how we come up with the differential equation here. So I'm going to do a little bit of a review, and we talk about once we get there where we go. And we're going to talk about the class of differential equation. This is here, but let's do a little review here. So again, we look at the circuit here for t greater than 0. Once the switch has moved, the inductor and the capacitor come back to the circuit because of that change, the switch motion. The switch has caused a change, so the capacitor now is back, and so is the inductor. Okay, and then we begin in nodal analysis procedure, identifying the nodes. I selected this as a reference node here. And then I labeled the other nodes, V1 and V2. And then I put current on my passive elements, which basically each resistor, inductor, and capacitor. We already had a current on the inductor, so I don't need to add another current to that. This is a case where we have no voltage source, so I don't need any source equations because there is no voltage source in this circuit. So I basically do a KCL at each node. That's not the reference node. So KCL at node V2 and V1 are basically there. When I do that, then I do Ohm's law for my resistor current. Okay. All right. So the two resistor currents are the Ohm's law. I use the Ohm's law into the KCL equations, that step called KCL plus Ohm's law. So you get these two new equations here. I put under the same denominator so that things are nicely, and then I collect terms. So I simplify things. Then I write the inductor and the capacitor relationships. Given the circuit that I have, the current to the capacitor is I2, and it's following the passive sign convention. So it's 0.8 dV2 dt. The voltage across the inductor is essentially V1, and the current is going the opposite to the passive sign. So it's minus DIL. The inductor has a 1 Henry minus DIL dt. So now I decide to bring one of them at a time. I bring the inductor in the first case into the, so you got now these two KCL equations and these two relationships. So I'm going to combine these four equations in a way to get my differential equations. That's essentially what that step here. So the first thing I do, I use the inductor relationship here. Okay. So when I do that, equation 1 here, so wherever I have V1, I'm going to put minus DIL dt in my 2 KCL equation. I have V1 right here and V1 right here. So right there you have, again, following here, you have V2 plus DIL dt plus I2 equals 0. Okay. And then in this particular case here, the second one here, I have 4V2 plus 5DIL dt plus 4IL equal to 0. Okay. At this point, I'm going to use the capacitor relationship, meaning wherever I have I2 in these two equations, 1 and 2 here, I only have I2 here, I'm going to put 0.8 dV2 dt. So I do that for essentially equation 1. You get V2 plus DIL dt plus 0.8 dV2 dt equal to 0. You should pause and look at, do you have essentially two equations, two unknown systems? Because we're going to be solving again for one pair, and I do, the unknowns are V2 and IL, essentially. So many ways sometimes you can do that. In this case here, there's a fairly obvious one. I can solve. You don't want to solve for something that's sitting inside of a derivative. So I solve for V2 from equation 2. So I solve for V2. So V2 essentially is minus IL minus 5 over 4 DIL dt. And then I use V2 into equation 1, and I get this kind of mess, but I get an equation. I collect terms, try to put under the same denominator, and then essentially combine my terms. And eventually I normalize such that the highest order derivative essentially has a unit 1 coefficient here, and I get my differential equations, okay? So when I get my differential equations, and I need to identify my alpha is this coefficient divided by 2. So what is essentially is that 2.1 over 4, and then my omega n is square root of 1, which is 1, okay? So this is the case, if I did my math correctly, omega n is larger than alpha. So I'm going to identify this as an underdamped case. Okay. So that's the case here. I'm going to go back to the PowerPoint slide to show you the final solutions once I've identified this as an underdamped case. Okay. But that's the typical process here that we go over, essentially embedding those relationships for the inductor and capacitor into our nodal analysis, typically KCL and source equations, to come up with one differential equations. So let me pause here and go to the PowerPoint to try to finalize this solution here. So we are again going to be solving this differential equation here. Okay, that's the standard differential equation where this term here is 2 alpha. This term is 2 alpha here. Omega n here is 1. Okay, so we can calculate alpha, and I'm sorry for the scratches here. So alpha is essentially this term divided by 2. That's what you see, the 2.1 over 4. So that's 0.525, and then omega n is square root of 1, which is 1. And then we've identified that obviously omega n is larger than alpha. So this is an underdamped example. So I'm basically going to now show you how to solve for the solution for an underdamped example here. Let me go quickly to the PowerPoint slide to show you what I'm talking about, and I'm going to go back to the slide and work on it here. So There is the solution on the PowerPoint, essentially slide. So we're looking at here a second order differential equations. So the coefficient associated with the first order derivative is 2 alpha, and the coefficient associated with IL in this case is omega n squared. Okay, so we identified omega n to be 1, square root of 1. We identified alpha to be 0.525. It's an underdamped example, and we can write the solution. Again, I know this may be a stretch for you as e to the minus alpha t, okay? Multiplied by a cosine omega d t, and omega d, by the way, is square root of omega n squared minus alpha squared. It's going to be 0.85 plus b cosine omega d t, okay? So I'm going to actually pick it up here and work things out a little bit on paper here. So let's go back. So we're looking at here right there. So again, what am I going to write here? I'm going to write the solution IL of t greater than 0 or equal to 0 is equal to e to the minus 0.525 t times a cosine 0.85 t plus b sine 0.85 t. Okay. So that's the solution for IL of t, straight from this here, looking at essentially the case where omega n is larger than alpha here. And of course, we have that, and our job right now is to calculate the two coefficient a and b, and we're going to use the initial conditions for a and b, essentially the initial condition on the current on the inductor, which is 1 amp, and on the capacitor voltage. You have got to remember the capacitor voltage is given by this. Okay, that is no small joke actually to get the capacitor voltage from this, because if you have to differentiate, in this case, you have to differentiate the dl dt. You got to remember the derivative of this, of a product of function derivative of the first multiplied by the second minus the derivative of the second multiplied by the first. Okay, so there's a fair amount of math in terms of getting the capacitor voltage from here, from this function here. That's done here. Okay, so, and I can show you that on paper. It's going to be a little laborious here, but let's try to do that here. So what do we have here? So this is essentially IL. So V2 of t is equal to minus IL. So what do we have? Minus 0.525. Oops. So minus exponent 0.525. So I rewrote things to be a little cleaner so that I don't make sense. So in a separate sheet of paper to make it a little bit easier to consume here. So we have the differential equations here and identify alpha. Alpha is, again, the coefficient associated with the first order derivative divided by 2. So that's 0.525. And omega n is the square root of the coefficient associated with IL here, which is 1. We've identified that omega n is larger than alpha, so it's an underdamped. And then we calculate that omega d, which we're going to need here. And then that gives us IL of t for t greater than or equal to 0 as e to the minus 0.525 t times a cosine 0.85 t plus b sine 0.85 t. Okay, so that's essentially the current, the function for the current. We now have to identify A and B, and we need the initial conditions for that. And where we go get this? We go get this from the previous solution here. We go get from V2, we're going to essentially express V2 in terms of IL, and this is not some small step. So I'm going to essentially try to do that here to show you what it takes to do that, even though it is messy. I want to work through the process with you. Okay, so V2, which is the capacitor voltage, is minus IL minus 5/4 DIL dt. Okay? So that's essentially V2 here. So I'm going to essentially work that out. So what do we have here? We're going to have V2 is minus e to the minus 0.525 t times a cosine 0.85 t plus b sine 0.85 t, okay, plus or minus 5/4 times the derivative of this. So let's work this way here. So what do we have here? We just minus 5/4, the derivative of the first. So we're going to minus 0.525 e to the minus 0.525 t, okay, times a cosine 0.85 t plus b sine 0.85 t. Okay, so that's the derivative of the first times the function. Plus the derivative of the second, what's in the bracket here, multiplied by this, all multiplied by this here. So minus 5/4 e to the minus 0.525 t, okay, times the derivative of this, okay? So minus 0.85 times a sine 0.85 t plus 0.85 cosine 0.85 b cosine 0.85 t. Okay, so this entire thing here is essentially what you got here from this function here from this. Okay, so you can kind of see things and you have to collect terms here. And if I did my things correctly, you have to collect all the terms. So we can actually factor it out e to the minus 0.525 t. We can factor it out. So, and collect the terms for cosine and the term for sine. So let's look at that. So this is cosine 0.85 t times minus a from this, okay? Then we're going to pick up what? Plus 5 times 0.525 a, if I did my things, over 4, okay? And then I'm going to pick up right here, I'm going to pick up minus 5/4 times 0.85 b. Okay, so that's just all of the term associated with the cosine 0.85 t. Okay, if I did my math correctly, obviously I provide some room for error right there. And then I go plus sine 0.85 t. And then I'm going to collect all of the part that associated with that. So I get minus b from here. Then we get right here. So I get plus 5 times 0.525 over 4 b right there. And then I get this part here. So I'm going to have plus 5 over 4 0.85 a right there. Okay. So it's a mess. I grant you that. But that's essentially what I'm going to be doing here. So this is essentially equal to V2 right there. And then we're going to say IL at 0 is equal to 1 amp. And when I do IL at 0 is going to call 1 amp. What do I get here? I'm essentially going to find that A is equal to 1. Okay. And then I go back and plug there and say V2 at 0 is equal to 0 and solve for B. And what you're going to find out if I did things correctly here, you're going to find that B is equal to minus 0.32. Okay. So the solution for IL of T is equal to e to the minus 0.525t cosine 0.85t minus 0.32 sine 0.85t. Okay. After I satisfied essentially the initial conditions. So that part essentially of finding V2 from IL is quite messy because it involves derivative and you know, and all these things. So you have to take derivative of a product of functions. But I apologize, but it is part of the work. So this is a good example. This is a robust example. Again, that part that we're looking at here is a solution. This is essentially your Math 45 differential equation solutions. Again, we had two initial conditions. We had IL at 0 equal 1 and V2 at 0 equals 0. These were our initial conditions right there. So we were essentially, we got IL from the differential equations, and when we worked in V2 from the circuit solutions, we could express V2 in terms of IL, and that wasn't so simple. And if we did our math correctly, and we enforce the initial conditions, and we get the solutions for IL. We'll pick up another example. This is a bit messy, I grant you that, but it also shows you that, again, it shows you the entire process from working the solutions for t greater than 0 using nodal, coming up with the differential equations, and then from the differential equations here, you essentially can proceed to solve write the solution, solve these constants using initial conditions, and so forth. Thank you.